All right, let's talk about collisions. You're probably taught that when two things bounce off each other, that's an elastic collision. And when they stick together, that's inelastic. But what if I told you that's not quite right? That the real story is actually way cooler.
Okay, so let's dive right in. Just picture it in your head. You've got two billiard balls. They click, they bounce apart, perfect. Then you've got a car crash, where the metal crumples and the cars get stuck together. The difference seems pretty obvious, doesn't it? One sticks, one bounces. But that's just scratching the surface.
Yeah, this is the rule most of us learn in our first science class. And look, it's not totally wrong, but it is seriously incomplete. It's kind of like saying all birds fly. I mean, it's a good rule of thumb, but you're missing out on penguins and ostriches and the deeper truth of what makes a bird a bird. So let's go ahead and bust this myth wide open. The real difference between an elastic and an inelastic collision has nothing to do with bouncing or sticking. It's all about energy. To really get this, you gotta know about two big ideas in physics. First up is momentum. You can just think of it as an object's oomph, how much motion it has. And in any collision ever, the total momentum you start with is always the same as the total momentum you end with. That's a rock-solid law of the universe. But then there's kinetic energy, the energy of motion itself. And here's the twist. Kinetic energy is the flaky friend. It is not always conserved. And that right there, that's the one true test. So forget about sticking and bouncing for a second. The only question you ever need to ask is this. Was the total kinetic energy the same before and after the hit? If the answer is yes, congrats, you've got an elastic collision. If the answer is no, it's inelastic. Simple as that. And this little analogy just nails it, right? If two things stick together, you can absolutely guarantee that kinetic energy was lost. But and this is the important part, things can bounce apart and still be inelastic. Just think about dropping a slightly flat basketball. It bounces, sure, but you can hear that thud. And if you could measure it, you'd find a little bit of heat. That sound, that heat, that's lost kinetic energy. So yeah, sticking is just the most dramatic, in-your-face example of an inelastic collision. Okay, theory is great, but let's make this real. We're going to walk through a classic sticky collision and see exactly where that energy goes. So here's our setup. We've got a small, fast block heading right, and it's on a collision course with a bigger, slower block heading left. And the key detail here is that we're told that after they smack into each other, they're going to move as one big lump. So how in the world do we figure out what happens? Well, we just use our first golden rule. Momentum is always conserved. We calculate the momentum of each block before the collision, remembering that moving left is negative, and we add them up. Then we set that number equal to the final momentum of the new combined block. A little bit of algebra, and boom. The math tells us they'll ooze off to the right together, really slowly, at about 1/3 of a meter per second. Okay, cool. We found the final velocity, so we're done, right? Not so fast. That only tells us what happened. To classify the collision, we have to pull out our energy litmus test. We've got to calculate the kinetic energy before the crash and after the crash and see if they match up. And when we actually run the numbers, whoa, the result is pretty shocking. Before the collision, the system was buzzing with 27.5 joules of kinetic energy. After, the new combined block has less than 1 joule. That energy did not just disappear. So where'd it go? A massive amount of that kinetic energy, we're talking over 95% of it, got converted. It transformed into other stuff. Imagine the crunching sound as they hit, the heat from the friction and the metal bending. That's your missing energy right there. And that is the whole point. The sticking is just a symptom. The real diagnosis is the energy loss. This collision is inelastic precisely because the kinetic energy was not conserved. All right, so we've seen energy get lost in a messy, sticky collision. Let's flip the script now and look at the opposite. What does a perfect, clean, elastic collision look like where not a single drop of kinetic energy is spilled? Okay, new puzzle. We've got a small block hitting a stationary block that's twice its size. Now, we're told it's an elastic collision. Our job is to figure out how fast each of these blocks is moving after they bounce off each other. The tricky part? We've got two unknowns, the final speed of block 1 and the final speed of block 2. Now, if you remember from algebra class, when you have two unknowns, you need two different equations to pin them down. And lucky for us, we've got them. Our first tool, as always, is conservation of momentum. But because we were told this collision is elastic, that hands us a second, super powerful tool, the conservation of kinetic energy.
Okay, now we're not going to drag you through every single line of the algebra here because it can get a little messy, but the technique is a classic. You basically solve one equation for one of the velocities, and then you plug that whole expression into the second equation. It's a neat trick that lets you get rid of one of your unknowns so you can solve for the other one.
And after the mathematical dust settles, here is what we find for the first block. Its final velocity is -1/3 of its original velocity. Now that negative sign is super important. It's telling us the block literally reversed course. It bounced backward at 1/3 of its original speed. And what about the bigger block that was just sitting there? It gets shot forward at 2/3 of the small block's initial speed. And in this perfect, idealized collision, every single bit of momentum and every last joule of kinetic energy is perfectly accounted for. Nothing was lost. It was all just redistributed.
Okay, we've looked at an inelastic collision, we've looked at an elastic one. Let's tie this all together now with the big picture. So, here it is, all laid out. The one thing to remember is that in any collision, momentum is king. It's always conserved no matter what. The real question, the one that sorts collisions into two different camps, is all about the kinetic energy. If it's conserved, it's elastic. If it's not, it's inelastic. Doesn't matter if they stick, bounce, or just kind of bump and keep going. And look, this isn't just some abstract physics problem. This is everything. It's how engineers design crumple zones in cars, which are built to have inelastic collisions to turn dangerous kinetic energy into harmless bent metal. It's how scientists understand what's happening when particles smash together at the Large Hadron Collider, which kind of leaves us with one last big question to chew on. That lost energy from an inelastic collision never really vanishes. It just changes its costume. So what other amazing energy transformations are happening all around us, all the time, that we don't even see?